Good afternoon. This is Group 16 presenting. My name is Akelo Sande Obonyo, doing number 1. When we read through number 1, this is the data that we summarize, of which what is in question is the conditional probability that a person in fact has a disease. So in the data, we have the probability of having the disease as 0.01, the probability of not having the disease as 0.99, the true positive rate as 0.90, then the true negative rate as 0.90, and the false positive rate as 0.10. So here we are going to use the Bayes theorem. In this Bayes theorem, as we see, we have all this, we have this, we have this, and we do not have this. So we have to calculate the probability of having a positive test, which is 0.108. And when we do our final calculation, we shall have 0.833. And when we convert it into percentage, we find that the conditional probability that the person indeed has the disease is 8.33%. Then number two, it's requiring us to find the probability of selecting a carton of sour milk, given there are 2 sour milks out of the total cartons, which are 10. So here we shall have just the expected outcome, which is 2, with the number of sour milk out of the total, which is 10, giving us a probability of 0.2.
Hi everyone, this is question Aisha and I'm going to take you through question 3, 4 and 5. So question 3 is, suppose Q and S are independent events such that the probability that at least one of them occurs is 13 and the probability that Q occurs but S doesn't occur is 91. What is the probability of S? So here we first define the unknowns, whereby we let probability of Q to be small q, probability of S to be small s. We apply, since they are independent events, the probability of Q and S both occurring is Q times S. The probability of Q occurring but S not occurring is Q times into 1 minus S. The probability of the union is Q plus S minus Q times S. Then we set up the equations by substitution method. Then when we use the substitution method, we get S to be out of 2 out of 9. Then at the end, the value of the unknown, which represents probability of S, is exactly 2 out of 9. So our probability of S is equal to 2 out of 9. So as we can go through the next question, question 4, a family has 5 children. Assuming that the family of a girl on each birth is 0.5 and the 5 births are independent, what is the probability that the family has at least one girl, given that they have at least one boy? So here, as you can see, the given that the number of children we have 5, probability of a girl we have 0.5. Then we get the total possible gender combinations, which is 2 power 5, which we get 32. Then we define the event. Since event A, a family has at least one girl, event B, a family has at least one boy, then the target, our target in the question, it is this one. So we calculate the probability of at least one boy. We get it from all girls, which is 1 minus 1 out of 32. Like all girls, we get 31 out of 32. Then now we calculate the probability of at least one girl and at least one boy. Since all outcomes of boys is equal to 1, outcomes for all girls is equal to 1, then the outcomes of both, and 32 minus 1 equals 30. Then we get 30 out of 32. Then our final calculations, we are going to get 30 out of 32 divided by 31 out of 32. Then the total answer, we are going to get the probability that the family has at least one girl, given they have at least one boy, is 30 out of 31. So when I take you through the question 5, if we randomly pick 2 television sets in succession from a shipment of 240 television sets, of which 15 are defective, what is the probability that they will both be defective? Both be defective, we are given data. Total television sets, we have 240. So defective television sets, we have 15. So we get the non-defective sets equals 240 minus 15, we get 225. Then the probability that the first TV is picked is defective is 15 out of 240. But then probability that the second TV is defective without replacement, we are going to get 14 out of 239 since it is without replacement. So the probability that they will be both defective, we are going to get the probability that the first TV picked is defective divided by the probability that the second TV is defective. Then we get the answer as 0.003266. Thank you.
Hello, my name is Haulana Matamwanaisha, and I'm going to be taking you through question 6 and 7. So, question 6, we have a poll of 500 people determines that 382 like ice cream and 362 like cake. How many people like both if each one of them likes at least one of the two? So, so if you can imagine, if we have like two sets, and then we have a set of people who like ice cream and a set of people who like cake. But then in the middle, we have a set of people who sort of like both cake and what? And ice cream. So they want us to determine that intersection, the number of people who like ice cream but also like cake. So what we are going to do, we are going to use this probability formula, probability A. Probability of A union B is equals probability of A plus probability of B minus the intersection. This is going to enable us find the probability of the intersection because we are looking for the intersection. So we were given the total number of people, which was 500. And then the number of people who like ice cream, if I say ice cream is A, and then we call that 382 people. And then the number of people who like cake, which was 662. So these numbers of people who like ice cream and the number of people who like cake are inclusive of the number of people who like ice cream and cake. So then substituting into the formula, we would then have uh, probability of A union B, which is 500, the total number of people, is equals to the probability of A, 382, plus the probability of B, which is 362 minus the intersection which we are looking for. And then when we solve, we shall be able to have 244 as the number of people who like both cake and ice cream. Then moving on to question 7, we were given a ball contains a box contains 5 green balls and 3 black balls and 7 red balls. So we were given 2 balls are selected at random without replacement. That is very important from the box. What's the probability that both balls are of the same colors? So we first map out our box. We are given the number of green balls are 5, then the number of black balls are 3, and the number of 7. The number of red balls are 7. So from this, we are able to find the total number of balls we have in the box, which are 15. And then probability of the same color. Remember, the question tells us 2 balls are selected without replacement, meaning we pick a ball and we do not put it back into the box we pick, and the total number of balls in the boxes keeps on reducing depending on on each given ball. You understand? So if we pick green, the number of green balls will reduce from 5 to 4. If we pick black, the number of black balls will therefore reduce from 3 to 2. Red will reduce from 7 to 6, and so on. So probability of the same color, the probability of both balls being the same color. So that means in the first picking we shall pick either green, and then in the second picking we shall pick another green one and green two. Then in the second picking we shall pick like if it's black we shall pick black one. Then in the second picking we shall have another black. Then if they're both red we shall have red one and red two. So we find those individual probabilities. So so first of all, so black one and black two, we shall find, let me start off with a green. The first green is 5 out of 15. Then the second one, since like the number of green balls have reduced, also the total number of balls have been reduced, the second picking shall be 4 out of 14. And then we multiply those probabilities, green one and green two. And that is why we have the multiplication. Then if both are black, we shall have the first one as 3 out of 15. Then the second one, the blacks have reduced, then the total number of blacks has also reduced. Total number of balls has reduced, so we shall have 2 out of 15. So black 1 and black 2, we multiply. We do the same for the red, and then we add the total probabilities. So the probabilities of both greens plus the probability of 2 blacks plus the probability of 2 reds. That is what gives us the probabilities of both balls being the same color. Thank you.
Hello, so my name is Esther, and I'm here to present. Number 8 and number 9 for this group. Now, number 8. First, let's just go through the question. The question says, find the sample space for a random experiment which consists of tossing a coin until the first head is obtained. Is this sample space discrete or not? Now, the first question, we first create a sample space. Now, this sample space is going to have, it's going to be preceded by a number of tails or no tails, and then it's going to end with H, so that in that way the first head is gotten. So you first list the sample spaces. So on head, on the first toss, it will be a head alone. Then on the second toss, a tail and a head. Then on the third toss, a tail and a head, or tail and a head, and then so on, really till n minus 1, till the nth toss. Yeah, so now it creates a sample space that looks something like this. So as long as a preceding number of tails, or even, for example, the first case without a tail, and then ending with an H. That's until the first head is gotten. So that's the sample space. Now, is this discrete or not? Now, this sample space is countably infinite. How are we able to do this? We're able to map it to natural numbers. When you map it to natural numbers till the nth time, hence it's countable, and it's infinitely countable. So hence it's discrete. Yeah, even if it's infinite, that doesn't change the fact that it's countable. Now for number 9. Number 9, it's similar to number 8. It's just that find a sample space of the random experiment, which consists of tossing a coin infinitely many times. Yeah, and then is the sample space discrete or not? Now here we did the same thing. Just that here the coin is tossed forever. It is tossed forever. So i.e., for example, the first outcome, it will come out, it can be H, heads and heads alone. Then for the second outcome, it can be tails alone. For the third outcome, it can be heads, tails. For the fourth outcome, it can be tails, heads. For the fifth outcome, it can be tails, heads, tails, heads. So the pattern, the sequence is continuous. It's infinite. You cannot count it. Now that helps us to answer our other question. Is this discrete? No, it's not. It is not discrete because it is uncountably infinite. So yes. So now why is it not discrete? Is because we cannot count the number of sequences. We cannot count the number of sequences that are made by this sample space, making it infinitely uncountable and hence not discrete. Yeah, so that's it from us.